So many x's, so many curves, and so many unknowns. The problems get longer and harder, but you don't feel like you're getting any smarter. Sometimes you wonder how the equations click and the formulas stick. Mathematics is not about yapping or memorizing, it's about recognizing. The number of variables to consider is too great to remember, but what if I showed you an easy way through the slumber? My name is Pihedron, and today I'll help you solve increasingly difficult puzzles using tricks only. Even if you're an expert, you learn something new when it comes to these mind-blowing discrete math, algebra, geometry, and probability riddles. Mathematics often begins with discrete countable objects. The first set of numbers we learn about are the natural numbers, so it only feels natural to start here. Alice and Bob have turned their attention to yet another activity that doesn't require touching grass. An endless hallway is lined with light bulbs. Each bulb is connected to a switch and begins turned off. Alice, after reading the guide, decides to flip every 40-second switch. Bob, for no particular reason, decides to flip every 69th switch. However, the switches have a fault. When a switch is flipped more than once, the bulb explodes. Which bulb will explode first? Pause the video to figure it out yourself. Nah, just kidding. Number theory problems can come in many forms, and light bulbs happen to be a common theme for them. When a person is set to flip every nth switch, only switches that are multiples of n are affected. For a switch to be flipped by both Alice and Bob, there must be a multiple of 42 and 69. Basically, we need to find the lowest common multiple of these numbers. Of course, you can write out the multiples of 42 and 69, but I can speedrun diamonds half a dozen times before you finish. The smart way is to factor our numbers into primes. The LCM will be each prime raised to its maximum exponent. Since any natural number raised to the power of 0 equals 1, if a prime doesn't appear in the other number, the power will default to 0. After multiplying these numbers, we get the correct answer of 966. Likewise, to find the highest common factor, we would just raise each prime to its minimum exponent. In a class of 20 students, 16 passed mathematics, 13 passed English, and 12 passed science. What is the minimum number of students that passed all subjects? Despite the simple premise of this problem, large language models seem to struggle with this a lot. So if you solve this problem, you're safe for now. This is a popular set theory question that requires surprisingly little math to solve. The key is to flip the question and ask what is the maximum number of people who failed any subject. To increase the number of people who failed any subject, we have to decrease the number of people who failed more than one subject. This means there will be a broad distribution of failures across the class, minimizing the number of students who could have passed all three. So to find the maximum number of students who failed any subject, we just add the number of fails for each subject, which gives us 19. This means there must be at least one student who passed everything out of the 20. Algebra is fundamental to most of math. Problem solving often involves forming and solving equations. Being able to visualize equations gives you an upper hand, especially in this problem. You are given the equation cosine of x equals min of y and 0, and your task is to construct an equation for the new graph after applying a series of transformations. Reflect the graph across the x-axis, translate the graph upwards by 1 unit, and stretch the graph along the x-axis by a factor of 2. At first, this seems impossible to do without drawing the graph first. You've never seen an equation containing both a trigonometric and minimum function. However, the operations involved in the equation are irrelevant when it comes to transforming the graph. The trick is to not move the graph, but manipulate each axis. Notice that stretching the y-axis actually makes the parabola shallower in this situation. This is clear once we normalize the plane to the correct aspect ratio. By reversing the order and applying the opposite transformation to each axis, we can transform the graph correctly. Stretching along the x-axis by a factor of 2 corresponds to halving x. Translating the graph up is the same as moving the plane down, so we subtract 1 from y. When it comes to reflections, you want to be careful because reflecting across the x-axis means you're only flipping the y position by applying a negative scale. Dividing by -1 is the same as multiplying by it, so we can move the minus sign to the front. We've somehow transformed the graph without touching anything else. Finding shortcuts during an exam can save you lots of time and effort. Many people often overlook the special properties of numbers, opting for a longer and more error-prone method. Try solving for a, b, and c in this equation. Most of us have never encountered an equation with 4 variables. Solving for 3 variables using a single equation seems impossible. A math student's first instinct would be to expand the brackets and collect the like terms for x. Equating the coefficients of polynomials is something we were taught to do in high school. However, we can do better by being more creative. When an expression is multiplied by 0, it is consumed by the 0. Adding 0 doesn't change the value of the sum, so it's ignored. Since the equation must be true for all values of x, we can substitute values of our choice to eliminate some terms and form simpler equations. By substituting x equals 1, both a and b are eliminated, leaving c by itself. Solving our new equation gives us c equals -3. Using a similar strategy, we can substitute x equals -1/2 to eliminate just a and get b equals -2. Finally, we can pick any value of x we want to solve for a alone. Geometry is a fascinating chapter because it's quite visual and is home to some of the best tricks. ABCD is a polygon, and O is a point equidistant to opposite vertices of the polygon. The area of opposite triangles are equal. The length of AB is 63, CD is 16, and AD is 56. Find the length of BC. The beauty of geometry is that it can be solved in many ways, but not all ways are equal. In fact, people tend to overcomplicate this problem, coming up with interesting but long solutions. Firstly, it's important to brush up on some trigonometry. The area of a triangle with 2 known sides and an angle wedged between can be found by treating one of the sides as the hypotenuse of a right triangle. The perpendicular height of the triangle is the hypotenuse times the sine of the angle. Following the formula for the area of a triangle, we get area equals half of a times b times sine of theta. Comparing the top and bottom triangles, we can conclude that the sine of the angles must be equal because the sides and areas are equal. However, the angles can't be equal because the sides opposite them are not equal. Looking back at our area proof, we can form a triangle with the same perpendicular height, using the same side lengths if the angles form a straight line. Therefore, angles AOB and COD must add to 180 degrees. We can replicate these triangles using the ABO and CDO pair. The same applies for the ADO and BCO pair, but with different angles. Let's try writing the opposite lengths of the quad in terms of the inner lengths. If h is the height of the triangles and x is the length of the segment connecting the height to the junction, then we can use Pythagoras to get the sides in terms of a, b, and x. Since the length of x is dependent on the angle and we don't know the angles, we want to get rid of it. Notice that the 2ax term is positive in the left equation and negative on the right. This means they will cancel out when both equations are added, leaving us with the following. Since the other pair of triangles must follow the same principle, we can deduce that the sum of the squares of opposite sides must be equal. 63 squared plus 16 squared must equal BC squared plus 56 squared, and solving for BC we get the answer as 33. You've been captured. There are 7 different boxes. One of the boxes contains a key to your cell. The 3 other prisoners in your cell are expert logicians like you. Each prisoner knows one attribute about the box containing the key. One prisoner knows the shape, another knows the color, while the last prisoner knows the pattern. Each prisoner knows which attribute the other prisoners were told, but you don't know which prisoner was told which attribute. You may ask each prisoner any number of times whether they know which box contains the key. They can only reply truthfully with yes or no. Any other form of communication is forbidden. Each box is equally likely to contain the key, and you only get one attempt to pick from the correct box. What is the probability that you succeed if you play optimally? The first step is to form a sound strategy for when you know which prisoner knows which attribute. Let A be the pattern prisoner, B be the shape prisoner, and C be the color prisoner. Ideally, you would ask A first because A would always say yes if the key was in the striped cyan circle, and no if it wasn't. There is only one striped box, so A would instantly know which box if the pattern was striped. If A said no, B and C can eliminate the striped box. Now B can confirm or eliminate the only remaining circle. The same idea applies to C. If all the prisoners say no, then you're certain it's the remaining four squares and triangles. However, you have to adapt this strategy to work with the situation where you don't know which prisoner is A, B, or C. All you can do is tell the difference between the identities of each prisoner. Your goal now is to question the prisoners in a specific order that gives you the most information about the location of the key. A viable strategy is to ask 3 different prisoners and repeat the same 3-person sequence until you get 7 no's in a row. If a prisoner says yes before the 7th no, we can stop asking. Let's see why this works. To eliminate the 3 easy boxes, we have to ask enough questions so that each prisoner gets the maximum possible information from the other's responses. The prisoner that requires the most information is C, since both the striped and red circles need to be eliminated before C can confirm or eliminate the red square. The minimum number of questions required is 7 because we have to guarantee a situation where C answers after B answers after A. In the worst case, A is the 3rd person we ask, making the first 2 responses useless. We must repeat our sequence to ensure B has answered after A. Then we must ask our last question to C, who finally has enough information to tell us whether it's the red square or the remaining 4 boxes. If a prisoner answers yes, we don't need to keep asking questions because as logicians, the other prisoners would know exactly which box contains the key as well. However, having less knowledge than the prisoners means we have to pick the box with the highest likelihood depending on the number of no's. The independent variables at play are the boxes and the order you question the prisoners. The possible responses you get from the prisoners depend on the 42 possible scenarios created by the 7 boxes and 6 permutations of prisoners. We already know that the prisoners will respond with 7 no's in 24 of these, so we only need to calculate 18 cases. For each case, we will write the number of no's we expect to get. This will help us group cases with the same responses from the prisoners and pick the box with the highest probability. For the striped circle, asking A first will immediately result in a yes, which means we should put a 0 in these cells. The other cells will be filled with the number of prisoners answering before A. The red circle is a bit more complicated because B can only say yes after A has said no. We might have to repeat some of our sequences to find a B that comes after A. For example, BAC, BCA, and CBA require us to ask B again, resulting in 3 or more no's. The red square requires C to come after a B that comes after an A to get a yes. This will result in more cases where the prisoners respond with lots of no's before we get a yes. After grouping the cases by the number of no's, we can determine which boxes have the highest probability for a given response. Groups with only one box guarantees us success for those cases, while groups with more will force us to make a guess. Our strategy will be to pick the box with the highest probability so the number of cases we win will be the max count for any box. Adding these up for each response, we get 12 cases where we win out of the 18. The overall probability for winning will be 12 plus 6, all over 42 because we can only guess right a quarter of the time for the 24 hard cases. In the end, this all simplifies to 3 over 7.
Well, that was the video. My name is Andrei and I'm glad me and Pihedron got to work on this project for the last month, I believe. We've both had our fair share of contributions, so if you want similar content, check out his and my channel. If you've enjoyed this as much as we did, you can support this video as a Summer of Math Exposition submission by going to the link in the description. Again, thank you for watching and as always, see you next time.